Good afternoon, Senior Management of EIU. We are Team 5. These are the things we'll be covering in our presentation. I'll first dive into the business opportunity. Currently in the country report, possible risks to political stability are highlighted and forecasted based on experts' opinions and analysis of the current political trends. Moreover, political stability is not quantified. Thus, to enhance the value of the country report, we believe that political stability can be forecasted using machine learning and quantified through the use of the Fragile States Index. By doing so, users of the country report will gain deeper and more accurate insights on the political stability of countries. So, what's the value of machine learning in the country report? Firstly, machine learning is an application of artificial intelligence which uses data and algorithms to imitate the way that humans learn, gradually providing more accurate and sophisticated responses. By integrating machine learning into its forecasting processes, EIU would be able to provide highly accurate and timely political forecasts in its flagship product, while saving costs and aging out its competition. Moving on, quantifying political stability and machine learning increase the value of the country report for its users who are mainly corporations, governments, and universities. Firstly, corporations use the country report to identify opportunities and risks of moving into new markets, as well as analyze and develop international entry strategies. When assessing markets, corporations don't only look at the economy's current health, but they also take into account its potential, which is heavily influenced by political stability. With the use of machine learning to forecast political stability, corporations would be able to better assess the future conditions of markets, thus making more informed entry decisions. Moreover, combined with the quantification of political stability, deeper and more objective insights of the current and future political conditions of each country would be generated. This improves corporations' analysis and development of customized entry strategies. Secondly, governments utilize the country report to monitor events in particular countries and view their economic and political trends from fresh perspectives. Quantifying political stability helps governments monitor and understand the political conditions of countries better. This enables them to identify countries that they can develop cooperative exchanges with and promote successful trade policies too. Moreover, forecasting spells out the potential long-term benefits of such exchanges. As the mentioned approach gives more objective and accurate results, governments that use the country report for fresh perspectives are able to view a fuller picture of the political issues at hand, thus aiding them in decision-making. Lastly, universities use the country report to assess comparable analysis and forecast of countries for international research. Quantifying and forecasting political stability using machine learning can generate more insightful and accurate forecasts. This strengthens universities' research. Moreover, as the quantification of political stability establishes a common ground for comparisons across countries, more meaningful comparisons can be made in their research. Moving on, machine learning gives EIU a competitive advantage. Currently, most of the firms in the advisory and forecasting industry do not quantify and forecast political stability using machine learning. As such, with the quantification and forecast of political stability as additional features of the country report, EIU will be able to stay at the forefront of the industry. Another value machine learning has is that the models used for forecasting can be customized to each class of countries. To give some context, we have classified countries into groups based on their income levels, and this will be further explained later. As different clusters of countries have different circumstances, the variable importance of independent variables differs across the classes. By customizing our models to each class, governments will be able to identify the sectors they should place more focus on. Consequently, governments will be able to allocate and utilize their resources more wisely to mitigate political risks efficiently. I'll now pass the time to Chi Hui.
To understand machine learning forecasting, we must first understand the differences between machine learning and non-machine learning methodologies. One key difference between them is the data sources used. Non-machine learning methods make use of historical time series data to draw patterns, while machine learning methods can handle much larger amounts of data from more diverse sources to produce more accurate and reliable forecasts. Another key difference is the way in which models created are validated. Machine learning validates a model based on its predictive accuracy, which divides data into train and test sets. It focuses on ensuring that the model is not overfitted, while the other validates its model based on a yes-no criterion using goodness of fit tests and residual analysis. Lastly, Machine learning methods can detect changes in patterns within a shortened time frame through automatic feedback of responses into its algorithm to detect hidden patterns that non-machine learning methods have a low chance of detecting. Here are some successful applications of machine learning in forecasting. One such example would be Walmart. Walmart successfully applied machine learning models to optimize the timing and pricing of markdown. Through machine learning, Walmart can better forecast demand and optimize quantity and location of its inventory. It has also employed machine learning that considers hundreds of variables in real time to recommend substitutes of stock items to consumers, resulting in a better shopping experience. From Walmart's successful application, it shows the viability of machine learning in forecasting to make accurate and adaptive predictions by taking new data points to further enhance and modify its algorithm to account for recent trends that old forecasting method cannot do without substantial labor hours. Another successful application will be Netflix's recommendation engine. Netflix used machine learning to develop personalized recommendation to each user using data generated by their viewing activities. Netflix also uses machine learning to determine which thumbnails have the highest chance for users to click on. This has enabled Netflix to personalize auto-generated thumbnails for every show and movie. From Netflix's successful application in their personalized recommendation engine and thumbnail, we can see that machine learning is able to generate specific reports and analysis for each individual user. With personalization, machine learning can account for differences between groups with differing circumstances, allowing for better understanding of how such differences affect the predicted output variables. EIU's flagship product of Individual Country Report currently uses historical data, different predictive models, and qualitative analysis by its expert analysts who have deep understanding of countries' specific situations. They are also supported by contributors who regularly report, review, and analyze recent economic and political events to produce analysis of each country from aspects ranging from political stability to economic outlook. Current issues of their methodologies are that it is rather labor-intensive and relies on subjective qualitative analysis to a certain extent. Machine learning can add value to EIU's flagship product as it can take in huge amount of data from different types and sources, and through its nature of iterative process, provide a more accurate prediction that considers recent changes dynamically. This will allow EIU to account for such changes in circumstances of each country with significantly less labor hours. Through machine learning, political stability can be quantified through the usage of fragile state index to improve comparability between different countries and show impacts different independent variables have on countries' FSI to produce more specific analysis on political stability for individual countries. Machine learning works based on garbage in, garbage out principle, meaning that if a machine learning model is fed with data of poor quality, the model becomes more complex, increasing computation time and decreasing the accuracy of its predictions. Therefore, it is essential to feed relevant data of good quality into models during construction. To ensure that data used in construction of machine learning models are relevant, two popular approaches known as forward and backward eliminations can be used. Forward elimination works on a basis where you start with nothing and successively add attributes, while backward elimination works by successively removing input variables from many. Through these approaches, relevant variables of high significance and correlation to the output variable can be sieved out and used in the training of the model. Other than ensuring relevance of variables, data quality of said variables are also very important. Sourcing data from credible sources and the process of data exploration and cleaning is also an essential step in the development of machine learning models.
Now, with all that in mind, let me show you the approach our group took to solve the business problem. So in order to develop a machine learning model for forecasting, we first needed to identify the dependent variable, which we will be attempting to predict. For this variable, we have selected the Fragile States Index, also known as FSI, and here's why. Firstly, the data is collected yearly. This allows for comparison against other years in a time series in order to determine whether the country is improving or worsening. The index processes data from three main streams by triangulating and reviewing it before giving it a final score. The content analysis stream applies hundreds of Boolean search phrases on articles, research reports, and other qualitative data from over 10,000 different sources so as to determine the level of salience of the issues the country is currently facing. The next stream is quantitative data, which represents pre-existing data sets from credible sources such as the World Bank, United Nations, and the World Health Organization. The last stream is qualitative review, where teams of social science researchers independently review each individual country to account for any anomalies. These three streams leverage on each approach's strengths to check for any other biases in the other streams, creating a robust index. The FSI originated from the Conflict Assessment System tool, also known as CAST. This framework was created in the 1990s for policymakers to better study and evaluate the drivers of conflicts, especially in complex and constantly changing environments. It is widely peer-reviewed and still used by professionals in the industry till this day, lending its credibility to the FSI. So The purpose of the FSI aims to identify and highlight the potential problems and warning signs to policymakers so as to help them in implementing effective policy responses to counter such issues. This is very similar to what our group is aiming to achieve with our project, which is to help EIU's clients gain deeper insights in order to make more informed decisions. And it is exactly why we have chosen it as our dependent variable. Moving on, these are the independent variables we have chosen for our model. Firstly, we selected the GDP per capita of a country as it is an indicator of the level of government funds available to ease and manage social and economic pressures. Next, we used the country's life expectancy at birth, infant mortality rate, and expected years of schooling, which are also used in the Human Development Index, which is an index that measures the level of development and strength of the country's human development fundamentals. And in conjunction with the Government Health Expenditure, Corruption Perceptions Index, and unemployment rate, it paints a holistic picture of how much effort the government is actually putting in to improve the standard of living for the population, encouraging healthier lifestyles, and securing the future of the country by improving accessibility to healthcare and education. So the level of effort will really be reflected on the satisfaction of the population with the government and affect the level of political unrest and instability within the country. We've also chosen to categorize the countries by income classifications. This is based on the GNI per capita using the World Bank's classification thresholds. The 4 classifications are high income, upper middle income, lower middle income, and low income. The reason for doing so is to find out the level of significance for each variable for different income classifications. This level may vary due to countries in different income classifications having different economic, social, and political conditions. Moving on, these will be the 2 machine learning models that our group will utilize for our forecasts. These models were chosen due to the continuous and quantitative nature of FSI. The first model will be a linear regression, which aims to establish a linear relationship between the dependent and independent variables. The model minimizes the squared forecast errors in order to achieve the best fit line. The second model will be a classification and regression tree, also known as CART. This model aims to continuously split the dataset into subsets based on a set of splitting rules until the subsets all have identical values, or when splitting no longer improves the accuracy of the prediction. However, this usually leads to an overfit model where the model is trained specifically for that dataset only. In order to create a more generalized and well-fit model, the splits must then be pruned using complexity penalties to penalize excess splitting. So through this project, we aim to demonstrate a proof of concept of machine learning by developing and training a predictive model to improve its forecast accuracy. In achieving so, we hope to showcase the accuracy and efficiency of machine learning, opening up opportunities for wider application in other products in EIU's catalog.
Next, data cleaning and exploration. Firstly, the FSI data was given in separate Excel files for each year. Thus, we combined them using Excel. We searched for datasets for independent variables and combined them with our FSI dataset using VLOOKUP on Excel. We then narrowed our dataset to the years from 2011 to 2018 due to the lack of data for some variables. Using R, we imported the relevant libraries, set our working directory, and imported our dataset using the fread function. Using the str function, we realized that our categorical variables, country and income type, were not of the factor data type, and we changed it using the factor function. We also re-leveled the income type from low to high income and ordered our data by year for clearer data visualization. We then used the summary function and realized that there were null and missing values. Some variables had a minimum value of 0, which is unrealistic as countries would not have 0 life expectancy nor 0 GDP per capita. Thus, these 0 values are likely to represent missing values instead. We also observed that some variables had NA values. These values could affect our results, and therefore we removed them by first replacing all 0 values with NA, and then removing all NA values using NA.omit. Next, to predict the FSI values of countries 1 year and 4 years later, we require countries to have all 8 years of data. This will allow countries to have sufficient data so that the first 4 years of independent variable values could be used to predict the FSI for the next 4 years respectively. Thus, using the dplyr library, we counted the years of data that each country has using the count function and removed those without 8 years of data. Lastly, we introduced FSI year plus 1 and FSI year plus 4 columns as the dependent variables by shifting back the FSI of countries by 1 year and 4 years respectively. We used the mutate function in the dplyr library to create these lag variables. And this is our final data set. Next, data visualization. Majority of countries have a FSI between 70 to 90, while the more politically stable countries have a FSI of around 20 to 30, and the less politically stable countries have a FSI of over 100. Countries with lower income have a higher median FSI, suggesting a relationship between income type and FSI. From the correlation plot, GDP per capita, HDI schooling, HDI life expectancy, healthcare expenditure, and CPI all have a negative correlation with FSI, indicating that an increase in these values would see a decrease in FSI. Infant mortality has a strong positive correlation with FSI, indicating that an increase in infant mortality would see an increase in FSI. Unemployment, however, seems to have little to no correlation to FSI. Implementing machine learning models. We will use these independent variables to predict our dependent variables FSI year plus 1 and FSI year plus 4 through linear regression and CUT. We will then categorize our countries according to their income type and use CUT models to analyze the variable importance to determine which variables are more important in predicting their FSI. Firstly, linear regression. We subsetted the dataset for the FSI year plus 1 model to years before 2018. Using the LM function, we train a linear regression model on the subsetted dataset and use the plot function to display the model diagnostics plot to analyze the three main linear regression assumptions. From the residuals versus fitted plot, residuals are equally spread around a horizontal line near zero, indicating that there is a linear relation between dependent and independent variables, and that errors have a normal distribution with mean zero. From the normal QQ plot, residuals follow the straight line well, indicating that errors have a normal distribution with mean zero. From the scale location plot, we see a horizontal line with equally spread points, indicating that errors are independent of the x variables and have constant standard deviation. From the residuals versus leverage plot, there's no data point that falls beyond the Cook's distance, which indicates that there are no influential outliers. The model diagnosis plots are similar for the FSI year plus 4 model as well. With these assumptions satisfied, we can now train our model. Firstly, we did a random train test split with a split ratio of 0.7, allocating 70% of the data to the train set and 30% to the test set. We then checked the distribution of our dependent variable is similar for both sets. Next, we trained a linear regression model on the train set and ran a backward elimination process using the step function to remove redundant variables to optimize our model. The model summary showed an adjusted R-squared value of 0.84, indicating a great accuracy of around 84%. Using the VIF function, we observed that all VIF values are less than 5, thus there is no multicollinearity. We then calculated the RMSE value of our train set. Next, we used the train model to predict FSI year plus 1 values for our test set and calculated the test set error by subtracting the true values from the predicted values. We then took the test set errors to calculate the RMSE for the test set, and these are our RMSE values. Subsequently, we predicted the FSI year plus 1 values for the train set and calculated the mean absolute percentage error for both sets using the MAP function. Taking Argentina as an example, we predicted the FSI for 2019 using 2018 values. We then did a similar process on our FSI year plus 4 model to predict FSI years 4 years later. We then used the model to predict the FSI for Argentina for 2019 to 2022 using the data from 2015 to 2018. Next, model evaluation. Our models have an adjusted R-squared of 0.84 and 0.83 respectively, indicating that they have over 80% of accuracy, with the FSI year plus 1 model being slightly more accurate. RMSE represents the standard deviation of prediction error from actual values. Since the mean FSI is 70.26, both models have a rather low RMSE of less than 10 for both sets, indicating low prediction errors. However, RMSE is scale dependent and is difficult to judge the RMSE value. Therefore, we measured the mean absolute percentage error, which is the percentage of absolute errors between predicted and true values. Both models have a low MAP of less than 0.15, indicating that the models are more than 85% accurate in predicting the FSI values. Overall, the FSI year plus 1 model is still more accurate with a higher adjusted R-squared value, lower RMSE and MAP values. Therefore, it is better in predicting FSI 1 year later. However, the FSI year plus 4 model is still useful in predicting the next 3 years of FSI values. This table shows how we intend to display our forecasted FSI values in the country report using our predictive models.
Moving on to CART, firstly, we'll be using sample.split for split ratio of 0.7. With 70% of our data to our train set, and the remaining 30% to our test set. Now we can build a CAD model for year +1 with train set as our data and complexity parameter of 0 for us to grow the biggest tree possible. And to prune our tree, we'll then need to find the mean CV error +1 SE. And with the use of loops, we'll then be able to find this optimal CP whose CV error is just below the mean CV error +1 SE. And now because of that, we're now able to find a geometric mean of two identified CP values in the optimal region. We'll then prune the tree based on this value to overcome the problem of overfitting. Now let's take a look at variable importance in prune model. Now we are able to compare our predicted values versus actual train set values and test set values. And with this, we are able to find an RMSE for both train set and test set. And here's an example on how we actually predict values for Argentina in 2019 in this case. Of course, this will be repeated for our FSI year +4 model with the exact same techniques but different data sets. And then we'll group our data by income type and apply the CAD model to each specific income type to obtain 3 different sets of variable importances as seen here. Looking at each variable importance, the ranking of importance of variables always changes. With this, we can actually see that the most efficient way to improve FSI in each category would actually be tackling unemployment in low and lower middle income countries, years of schooling in upper middle income countries, and GDP per capita for high income countries. This also means that it may not be as effective for low income countries to be adopting policies from high income countries, as their resources could have been better spent elsewhere. And to optimize efficiency in the long run, the most valuable investment would actually be 2 years of schooling, as it fluctuates amongst the top 2 positions in terms of importance to determining FSI. Moving forward, our team has chosen CAD over linear regression due to its potential to produce more accurate results as seen in the lower RMSE in both models, and its ability to rank variables affecting FSI. Linking back to our consumers, our analysis would benefit corporations and governments the most, in terms of generating profits or attracting investors. For corporations, we can predict political stability, which assists them with their investment planning, or to avoid countries that could potentially face political instability. Whereas for governments, we can identify important variables through variable importance, and identify the best approach through our overall analysis, such as the focus on unemployment and years of schooling for lower income countries. Moving on, we have our limitations and future directions. For limitations, the first problem we faced was the lack of data. This actually has resulted in CAD having a hard time considering smaller changes, which results in the predictions of FSI over the years for some countries to be relatively constant. Our model may be outdated as time passes by due to the volatility the world faces. Variables that were once relevant in explaining FSI may change. And lastly, instead of income types, there may be a more optimal way to categorize the country in the future that could bring about better insights in variable relationships. Now, looking at our potential pilot studies at EIU, with EIU's myriad collection of data, it will not only enhance our model, but also give us the ability to perform country-level analysis, as we now have the sufficient data to do so. This also allows us to customize our model based on consumers' needs. We plan to work with the analytical team in this field to generate better categorization for the country. And we will also be able to leverage not on just income type, but also other forms of categorizations for insights. Of course, with machine learning, we can expect more cost and time saving for EIU. What was previously done through manpower can now be done with a click of a button. Moving on to future directions, our team plans to take on an adaptive approach for our project. We have taken into consideration the volatility of the world in a future where years of schooling could be relatively the same throughout all countries. We would then need to take a look at other alternatives such as the quality of education instead. Furthermore, with the research and development in machine learning, we can expect better supervised and unsupervised machine learning models in the future, and we hope to utilize such an advantage. Lastly, we will be looking at quantifiable elements, new ones. For example, Global Health Security Index that was introduced in 2019. We hope to incorporate that into our models in the future. As previously, it was difficult to consider the readiness towards a pandemic in terms of numeric or categorical terms.
Thank you, Liang Ying. In conclusion, machine learning is effective in forecasting political stability of countries. This is evidenced by the moderately high accuracy of our linear regression and CAD models. With the high forecasting accuracy and the adoption of an adaptive approach, we believe machine learning can increase the value of the country report and thus is the future of EIO. We have come to the end of the presentation. Thank you.